Thank you for downloading this episode of In Our Time. For more details about In Our Time and for our terms of use, please go to bbc.co.uk/radio4. I hope you enjoy the programme. Hello, the star 51 Pegasi is part of the constellation Pegasus, and at this time of year, in clear conditions, it's just about visible from the northern hemisphere. To the naked eye, it's an unremarkable little star, but in 1995, astronomers discovered something extraordinary about it. 51 Pegasi is orbited by a planet. That discovery 18 years ago was the first time a planet had ever been detected orbiting a star similar to our own Sun. Planets orbiting stars outside our solar system are known as exoplanets. Less than 20 years after the discovery of the first exoplanet, scientists have confirmed the existence of more than 900 of them, with over 1,000 other possible candidates also identified. So how is it possible to detect bodies so distant that they're invisible to even the most powerful telescopes? What can we learn about them? And what are the chances of finding one that's capable of sustaining life? With me to discuss exoplanets are Caroline Crawford, Gresham Professor of Astronomy and a member of the Institute of Astronomy at the University of Cambridge, Don Polacco, Professor of Astronomy at the University of Warwick, and Suzanne Agren, Lecturer in Astrophysics at the University of Oxford and a Fellow of All Souls College. Caroline Crawford, people have been trying to find planets orbiting remote stars for centuries. Why is it taking anyone so long to get that, to do it?
I think the problem is that you're looking for something that is inherently, in astronomical terms, very small, very cold and very dim. And it's really taken us many centuries to get to the point where we've got sophisticated enough instruments, detectors and large enough telescopes to detect them. Because the idea that there could be undiscovered worlds out there is not new. We've thought about that for centuries. And certainly by the time we're discovering new planets in our own solar system, it kind of moves from speculation to, quite believable that there could be lots of other planetary systems around other stars. But as you say, it's only in the last 20 years that we've really moved to the stage of new exploration where we're discovering them almost every week. And the problem is that a planet, the planets we see in our own solar system with the unaided eye or with the telescope, we see mainly by the light they reflect from the sun. And so you might naively think that would be the best way to take a picture of a distant star. You would see the planets around it. But in practice, it's very difficult because the light that the planet reflects is very tiny, it's very dim. And it's not just that, you're seeing it right next to a really bright star. And detecting the light that the planet reflects wouldn't be a problem if it wasn't for the fact it's just swamped by the glare of the star. The analogy that we often use is that you could detect the light of a single firefly, but not if that firefly's right next to a car headlamp. And so you can't just by going and pointing your telescope and taking a picture of the star discover the planet around it.
And so we've seen a massive development. One of the key things is, often in science, technology leads science, doesn't it, sometimes? So the massive development of telescopes. Could you give us some idea of the force of these telescopes?
Well, certainly the thing is that this is a field that's completely observation-driven. You need very precise measurements, you need repeatable measurements, and you're detecting such faint light. You've got to block out the light of the star if you're doing direct imaging. You need to account for variations where the atmospheres maybe would blur your images. And this is why some of this science is now done from space telescopes and satellites. But it requires the biggest telescopes and the most accurate, what we call resolution, the ability to separate the light from one object from another. So it, again, is very much driving some of the current telescopes and technology and instruments that are being put on them.
They're extraordinary pieces of engineering, aren't they?
They're fantastic. And just the current generation of telescopes, you're talking, mirrors that are 8-10 metres across, let alone the next generation that we're looking at, where they're going to be far bigger. And it's not just the size of the telescope, it's the instruments you put on the end, the detectors, and all of that is really cutting edge. And that is what we waited so long for, to be able to detect these exoplanets.
Don Polacco, after centuries of being confined into our own solar system and even more limited, just with one or two planets around us, it wasn't until quite recently that we discovered Uranus and planets like that in our own system. A star like our own sun was found in the 1990s. How was this discovered, and what was it? How did they discover that star, which, as it were, set the galaxy rolling?
Yeah, this was an interesting experience because when it was first announced, there was a lot of scepticism. And the reason for that was that people had, for many years, thought solar systems would look much like our own.
Yeah.
So to find a Jupiter-massed object in a period of 4 days, that's 4 days. Remember, Mercury has a period of 88 days and Jupiter a period of 12 years. We didn't expect it. And so there was great controversy at the time. People thought this was actually a phenomena to do with the star rather than a different body. And I think that argument went on for 3 years before it was generally accepted. And during that time, other examples were found, things like 51 Peg, that could only really be interpreted by a planet. But there's a lesson in this for all of us here, and that is that if we take an idea of what we're looking for out into our observations, we could be wrong. We're biasing our observations. Other solar systems, the most easy solar systems to detect, do not look like our solar system.
That's what I found from reading for this programme, which is most extraordinary, because we think if we find another solar system, it's near enough like our own solar system. They're all over the place. There's no consistency. It's wonderful. I mean, there are 100 billion stars. Perhaps there are 100 billion variations.
Well, I think that's exactly right. And I think having preconceived ideas is dangerous in this game.
Can we just go back, Don, to how this first exoplanet was found, what method they used? Because we're going to talk about several methods used through these magnificent telescopes to get there.
Well, ironically, the first planet was actually found with an old telescope and quite a small telescope. But what was groundbreaking with this was the instrument. It's called a spectrograph, and basically it allows you to break the light up into its various colours, and it does it incredibly accurately, as Carolyn said, but it also does it in a really stable way. So if the temperature changes, the colours stay in exactly the same positions. And what these researchers were doing, these Swiss researchers were doing, were looking at stars and seeing if they changed at all. And they had a whole program looking at a number of stars, and they found this one that seemed to change very slightly.
Change what?
So what happened was the light would appear to be slightly blue shifted and slightly red shifted. Now what that means, it means the blue shift and the red shift. I'm sure you've heard of red shifts before. These are just signs of motion in the star. So if you imagine, let's take an example of two skaters. If you've got a massive one and a less massive one holding hands, and as they rotate around each other, as they spin around each other, the massive one hardly moves at all. It's in a very small orbit, while the smaller one is in a much bigger orbit. So the same happens in these solar systems. The stars are hardly moving at all. They're rotating around the common centre of mass, and the planet is moving in a big orbit. Now, just to put some flesh and bones onto this, to tell you what you're measuring a velocity. At some points, the star is coming towards you, and at other points, it's moving away as it rotates in its orbit.
Yeah. And out of that measurement, for that tiny amount of time, you can build all sorts of facts about it.
Well, you can see how this changes with time, and it tells you about the orbit. It tells you about the period of the planet. If you know the mass of the star, which we can get by estimating the kind of star it is, you can get the mass of the planet to some extent. And there are various other things you can find by that technique as well.
There are other techniques, so there were several, so we'll go through one or two of them. There's what I think is called here the transit method. Can you try to enlighten us, or can you enlighten us about that?
I certainly can.
Good.
So a transit method is very simple. It really is. Well, what I like about it is it has hardly any physics in, which is great. Because physics is always our downfall, right? But basically,
are you speaking for yourself here? No?
Well, this is me, right?
The royal we get out.
So the transit technique is wonderful because basically what we have, if we have an orientation of an orbit so that the planet moves across the face of the star, then the star will get slightly dimmer. So if you remember a couple of years ago, Venus moved in front of the sun. And there was a big hoo-ha about it because this doesn't happen very often. and people observed it, and you saw these pictures of discs, black discs on the face of the sun as Venus moved across. Well, the same thing happens with stars, except, of course, we can't see a disc, but what we can measure is the change in brightness. And you can imagine then that the bigger the planet, the more the star is obscured, so the bigger the dip in brightness, and the smaller the planet, the smaller the dip. So it's a nice, relatively simple measurement to make. Unfortunately, technically, it is really hard to make. So to give you an example, if you took a Jupiter-sized object, it would cause a dimming of about 1%. Right, so that's not an easy thing to make. If you want to take an Earth-sized object, it's a lot smaller.
Yeah.
So now the great thing about the transit technique compared to everything else is, as I just said, the size of the dimming is related to the size of the planet relative to the star. So you can actually get the size of the planet.
What amazes me is you have so little time to make, as available as it were on the results you get, to make these massive come to these massive conclusions. It's extraordinary. Can I have to turn to Suzanne Agron now? How does this method help in finding stars that have more than one planet orbiting them?
Well, you can use transits to detect stars with multiple planets around them in two different ways. One of them, which is perhaps the most obvious, is that there may be more than one planet transiting across the star. For this to happen, all the planets have to orbit in exactly the same plane. One of the prominent instruments that's been detecting lots of transiting planets in the last few years is the Kepler mission, which was a mission led by the NASA space agency. And one of the most exciting results from Kepler has been the detection of many of these multiple transiting planet systems. But another way to look for additional planets in the system is to monitor the transits. You have to observe for a long time, so you see many transits of a given planet. And if that planet was the only planet in the system, you would expect these transits to repeat at exactly the same interval, to be precisely periodic. But if there's another planet tugging on the planet that's transiting, the transits will not be exactly periodic. They will wobble a little bit in time. And this is a way of detecting a non-transiting planet in addition to the ones that transit. And this is actually a method that's analogous to the discovery of Neptune in the solar system. So Neptune was discovered because it perturbed the orbit of Uranus. And its position in the sky was predicted on the basis of observations of Uranus. And then it was found at the predicted position.
So that's where we are. I'm going on to one more method, the gravitational microlensing. Could you tell us about that method?
Right.
Because a lot of things are being brought to bear in this. We're at the beginning, and the excitement of this is that we're at the beginning of a new age of discovery, which the unexpected consequences of which could be enormous for us personally and globally.
Yes. So the microlensing method is perhaps the only method we haven't alluded to that's one of the major methods for detecting planets. And its particularity is that it enables us to look for planets which are relatively distant from our own solar system.
What are we talking about distant? I know these are baffling numbers, but we might as well have one or two of them.
Well, I think the most distant... So most of the planets that are found by the radio velocity method, which is the first method that Don discussed, are within a few tens of light years, maybe a few hundred. Transiting planets are within a few hundred or maybe 1,000 light years of our own solar system, whereas planets found by microlensing can be halfway across the galaxy, so several thousand light years away, if not more. Microlensing is a phenomenon which occurs because mass has the ability to bend the path that photons, that light rays, take when they reach us. And so if you have one star that's moving across the sky, and between us and that star is another star, and the light from the background star has to come past the star in the middle, then the star in the middle will bend it, and that will act like a lens. So if you are just looking in the direction of that star, what you will see is the brightness of the star gradually increase and decrease again. And this takes place over quite a long time, typically 100 days or so. We're interested in these events for a range of reasons, but if the lens star in the middle has a planet going around it, then that will cause a perturbation to this microlensing light curve. And what's interesting about these microlensing events is they enable us to take to discover planets which are relatively small and relatively far away from their stars. So they enable us to detect types of planetary systems that we're not sensitive to with other methods.
In a very short time, we seem to have gone literally and in scientific terms a very long way. Do you feel it's just at the beginning? There's more and more technological inventions which will carry us further, get it more accurate, open this thing up massively. That this is just the very beginning. This is A in the alphabet of astrophysics.
Oh, absolutely. I think that, starting 20 years ago, we've been essentially uncovering a new component of the universe, and there is a huge amount to be learnt about it. As you said, there's a lot that we can do because of new technology. There's also a lot that we can do because of new insights from theory. We shouldn't forget that the observations drive new theories about the way these planets form and evolve, and these theories make predictions that we then go out and test. So they give us some guidance as to where we should be looking.
Caroline Crawford, it seems that some exoplanets are easier to discover than others. So what dictates how easy it is to discuss a remote planet? Suzanne has spoken just en passant of halfway across the galaxy. So where are we there? I mean, what are we getting from that far away?
Well, as you say, different techniques have different strengths and have a bias, inherent bias to finding different kind of planets. Finding planets by either the direct imaging I mentioned, the gravitational microlensing Suzanne's mentioned, they're not yet the most efficient techniques. It's the two methods that Don has mentioned, which is the transit and that radial velocity technique where the star's moving. Those have been the primary workhorses. Those are where most of our exoplanet discoveries are coming from. And in the initial stages of any search, you're going to have a bias for finding a certain kind of planet which is going to be bigger because it's going to block out more of the star's light, more massive because it's going to produce a bigger gravitational tug on the star and make it move more. And they'll also orbit close to their star. So you get a repeating signal on the basis of a few days. And so in the early stages, we're finding these objects like 51 Peg that Don mentioned, which are large, massive, and orbiting very close to their star. Those have been the easiest ones to find. It's only now that we're beginning to get to finding other systems, but our samples are still completely biased to finding compact planetary systems dominated by massive planets. It's only now that we're kind of breaking away from that. And, again, there's differences about different techniques about whether you find stars and planets a long way from their stars. But at the minute, our samples are still quite biased.
Don Balaco, which brings us to the subject of hot Jupiters. Could you explain why they're relevant?
So the 51 Peg is a hot Jupiter, and what that really simply means is that it's a Jupiter-massed object that's being heated because it's so close to its star. Very simple. The thing is, we didn't expect to see them because they're
not really in our solar system allowed to exist, are they?
Well, not at the moment. No, that's true. But the reason they exist is because another problem we've had is that we thought the solar system is quite a stable area. But these are dynamic systems. These hot Jupiters were not made so close to their star. They had to have been made a long way from their star. And somehow they have migrated in to these central regions.
When you say, I'm not being silly here, but when you say somehow, you mean as yet you don't know?
Sorry?
When you say somehow, you mean as yet you don't know why they migrated in?
Well, we have ideas, and there are some leading ideas.
Yeah.
So, for instance, if you have some more planets in the system or even another star, there could be a gravitational interaction that forces that planet into its inner regions. There's also ideas that these things are made in a nebula, and somehow they've exchanged momentum in the nebula and moved in.
Could you just be a bit more graphic about hot Jupiters and tell us exactly what size they are, where they are, and why they're significant?
Well, they're significant because they're the easiest to discover.
Right.
So they were the first ones we found. They were the easiest to see. They also have a lot of mass in them, so there's a lot of planetary mass hidden in these things. Who's to say a lot of stars may have merged hot Jupiters that have not stopped moving in and have accreted into the star. So they're important objects, and I think we're beginning to understand them now.
But they're massive, aren't they, these hot Jupiters?
Jupiter mass.
Suzanne Agron, so we've talked, both Caroline and Don have talked about the mass objects. I mean, this is just skimming through, but still, that's what they've been trying. Obviously, it would seem now easy to find, and there they are now. How do you think it's going to be possible to find smaller types of planet like the Earth?
Well, we are already starting to find smaller planets, including planets which have a size similar to the Earth or even smaller. At the moment, the best way to do this is to use the transit method that Don described earlier, and to do it from space. Because if you try and do it from the ground, although we are still getting better at doing this all the time, the atmosphere limits the precision that you can measure the brightness of the star to. And also, every day the sun comes up, so you have to interrupt your observations. Whereas if you do it from space, you can make more precise measurements and you can do it continuously. So you can start to find planets which are both smaller and cause a shallower dip, and which are in longer periods because you can observe continuously. So the Kepler satellite, for example, has uncovered a huge population of planets with sizes between, say, 1 and 4 times the size of the Earth, so between the Earth and Neptune in size. And we now know that these planets are incredibly common. 1 in 5 to 1 in 6 of all the stars that Kepler has looked at has at least one of these planets.
Kepler is the new telescope.
Is that telescope?
State-of-the-art telescope, just a couple of years old, and it's changing.
It was launched in 2009 and it operated for just over 4 years. It's stopped operating now. But so these small planets are incredibly common, and we are now able to find them. It's still very difficult to find planets which are real analogues of the Earth, which are orbiting, which take about a year to orbit their stars, and which have a surface temperature similar to that of the Earth, which is a very important factor.
Do you think, Caroline, it's slightly biasing, as Don said at the very beginning of the programme, it's biasing your research to keep looking for something that's like us? Does that tug you back into a certain area of thinking?
I think it does, because you've got all those fundamental questions about how unique we are. I don't think any astronomer would argue that the Earth is terribly unique anymore. There's plenty of places where there could be planets, not necessarily an identical twin, but near enough to Earth out there. It's just actually finding them, as Suzanne says. That's we're not quite there yet. We're getting a few candidates which are getting close. But
you seem to be there with super Earths.
Certainly we have super Earths, and these are fascinating because, again, as Suzanne said, it plugs a gap. In our own solar system, you've got the largest rocky planet, which is the Earth, and then you scoot right up to Neptune, which is 17 times more massive. And in so many of these other planetary systems, you have these super Earths. They're kind of like between 2 and 10 times the mass of the Earth and about twice as big.
But are they rocky planets as well?
Well, again...
Or are they gassy planets or icy planets?
You get a combination. Some appear to be rocky, some appear to be gassy. There seems to be a crossover. And so this is a fascinating regime that we can't sample close at hand in our own solar system. But it's clear it's incredibly common out there. And the question is, we don't know how like the Earth they are. They could be temperate, they could have an atmosphere, they could have water, depending on their development and history. But they would have enormous surface gravity. So, about like twice the gravity you get on the surface of the Earth. So perhaps that maybe would be where the similarity would disappear.
But what's fascinating is the tentativeness of what you're saying and Suzanne's saying to a certain extent, and what Don's saying, is something that will be revealed later with more technology. You're on into a new area that's open. It's a completely new area of knowledge that's out there. Fantastic area of knowledge. And as we know from this programme, I mean, from you know probably because it's in your area, areas of knowledge which seem to be just areas of investigation turn out to have the most massive impact on every part of the way we live.
And I think a key thing about this whole area of research is that we are now moving from the phase where we're not just finding exoplanets, we're characterising them, we're understanding their properties and their differences and their similarities. And for scientists, that's the really exciting stage.
When we bring in brown dwarfs, Don Palacco, where does that take us?
Yeah, so brown dwarfs are quite interesting. They're like failed stars. To make a star, you need to have a certain mass. And you can go through the formation process for a star and find you don't have enough mass, and so nuclear reactions can never start. So brown dwarfs are out there. We've known about them for 20 years now, 30 years, and they can also have planetary systems of their own. So these are quite interesting because these are different to stellar systems, but planetary systems nonetheless. So brown dwarfs, they seem a lot like planets, but they're not. They're more massive. They've probably gone through a different formation exercise, but yeah, it's just another facet of everywhere we look, there are planets. So,
But do they bring anything? Do they bring anything special to the table at the moment? Because this discussion, as in terms of all your investigations, is very much at the first stages, and it's the fastest growing part of astrophysics, isn't it, or whatever it is. Right. But what do brown dwarfs give you that nothing else does?
well, brown dwarfs are things you can study the weather patterns on at some level, and maybe that's applicable to hot Jupiters and other large planets as well. So there are ways of studying similar phenomena that we just can't, that are much more difficult to study in planets. I don't know, Suzanne, if you want to.
Yeah, if I can comment on this briefly. So brown dwarfs have a typical size which is very similar to the size of a Jupiter size planet. They also have temperatures which are very similar to the temperatures of these hot Jupiters we were talking about earlier, but they don't orbit around another star. They're on their own, and we can therefore study them in more detail than we can the hot Jupiters, or at least it's easier. So we can use them, if you like, as templates to understand the physics of the atmospheres in particular of exoplanets, and we can see how they differ from planets, and the difference is going to be due to the influence of the star. So it allows us to basically take the star out of the equation and see what happens.
It'd still be great for me to know how, in a sense, so little evidence, there's little bleeps of light, if light can bleep, all right, passages of light, you're able to build so much solid information.
So a lot of the... So one of the things that happened in the last 10 to 15 years that I think very few people would have predicted is our ability to study the atmospheres of these exoplanets. And we have to remember that we never actually see the planet. We are doing everything through inference by indirect means. Right. And most of the information we have about exoplanet atmospheres comes from transit observations. So when the planet passes in front of the star, we can measure how large it appears to be. By how much of the light from the star occults. But if you can make this measurement in different colors, then you can basically look at how, if you like, you can measure the altitude at which the atmosphere becomes transparent in different colors. And if there are gases in the atmosphere of the planet or clouds, they will alter the altitude at which the atmosphere becomes transparent, and it will not be the same at all different colors because different gases absorb light of different colors. So using this method, which is known as the transmission method, we've been able to infer the presence in particular of clouds and certain atomic and molecular components in the atmospheres. There are other types of measurements which probably would take too long to describe in detail, but basically we are now starting to be able to have quite a precise picture of the temperature and composition of a very small number of particularly favourable exoplanets.
The very first exoplanet that was claimed to be discovered, it was in 1988, and it was a planet orbiting a pulsar. What place do pulsars play in this adventure? So
pulsars are interesting because they represent the end state of the evolution of a certain kind of star, a star a little bit more massive than the Sun. So when stars run out of fuel, they start to collapse under their own gravity, and if there's nothing to stop this collapse, they'll eventually reach the stage where all the neutrons are pressed together and they're resisting further collapse, and that's something called a neutron star. Now, if that neutron star is spinning very fast and has a large magnetic field, then it will have a jet of light and radiation coming out of the poles. And as the star spins, this jet will, depending on how it's pointing relative to the Earth, this jet will spin past the Earth once per rotation. And so we will see a periodic pulse of light, and that's known as a pulsar. Some of these pulsars have extremely short periods, down to milliseconds, and so they act as extremely precise clocks. And if the pulsar has a planet around it, then the planet will tug on it, just in the same way as planets tug on normal stars, and it will cause a slight variation in the timing of these pulsars because the light takes longer to reach us if the pulsar is not quite at the same distance. So there's only 2 pulsars that are confirmed to have a planet, but one of them was actually the first exoplanet to be found. It was in 1992 by Volkshan and Freyl, and it is a we don't know exactly how the systems around these pulsars formed, it's not clear that they actually were there before the star went through the late stages of its evolution, because it must have gone supernova, and that's a very violent explosion. It's not clear that a planetary system could survive this. So,
sorry, finish, please.
all I was going to say is they are not typical planetary systems, but they represent an interesting possible other means of forming planetary systems.
Caroline, can we talk about other properties of exoplanets it's possible to arrive at through observation, just so we can get some faint idea without seeing the subject, rather like you not actually seeing the planet you're talking about so authoritatively. Anyway, never mind. Can you say what observation is leading us to?
Okay, well, just to go through a list, from how often the signal repeats, you get an idea of the period of the orbit of the planet around the star. That'll tell you something about its distance from its host star. From the transit method, you get the size of the planet relative to the star. Combine that with the radial velocity method of, if you're able to do observations of the same system, you get the mass of the star. And Susanna's mentioned that we're now getting the chemistry, the atmosphere in some cases. Now, if you've got the mass and the size, you can start knowing stuff about the density of the planet as well. And so this is why we're quite confident to say, such and such maybe has it's a rocky planet, must be a gas giant, but also we see this huge disparity in densities of planets. I think the kind of extremes you get, Corot 6b, can't remember quite his name. 7, thank you, is 2.5 times.
What is Corot? Sorry,
it's the name of a planet. Sorry, they've all got these telephone numbers.
Why it's lovely that it's either Greek or French painting.
This is named after that's named after the satellite that made the discovery, right. And it's the star number of the observation of that satellite. But anyway, Corot 6b is something like 2.5 times the density of lead. So you have a planet that density at one extreme, and then some of these supergiants, hot Jupiters, can be, down to about 1/3 of a gram per centimetre cube. That's probably the equivalent of balsa wood or cork. Again, incredibly lightweight planets. So you again get this huge range of properties that you can tell.
Don Palaka.
I think what's also, just to add to that, what's really interesting is you get planets of the same mass that have completely different densities. Mm-hmm. So we get these Earth-like planets that have densities like lead or more, and then we get Earth-sized planets that are like fluffy balls. And no one really understands these at all.
Can we stick with this for a moment? I mentioned it earlier in the programme, and it was from your notes anyway, or somebody's notes around the table. But there's the variety that you're encountering. In terms of one theory fits all went out of the window in the first few years or year or two, didn't it? I mean, it's now more and more differences. Huh?
It should have gone out the window.
Can you just give some idea of how that figures in the sense of organisation inside your mind? Because we're used to organising things, aren't we, in these ways, from Newton onwards, almost neatly looking at what's happening now. But there seems to be, it's rampant out there. Things are going backwards, forwards, up and down. They're doing things previously people like you thought could never believe would be done. Can you give us some idea of the... Anyway, I've said it.
It's what we do best. We classify. That's the human condition. We classify things. But the situation we're in is that, in actual fact, there's only a small number of small planets that can be characterised in this way. There are lots of hot Jupiters, and there's great diversity in hot Jupiters, and there's physics going on in hot Jupiters that we don't understand. But in terms of small planets, there's only a handful that can really be characterised. So if you imagine there's lots of different possible configurations for a planet, well, we're just sampling a few of them. It's only when the big book is written and we have a lot more objects that we can start looking at families of things. And it's at that point we really begin to understand why our solar system is the way it is.
But Caroline, for a moment. One of the things that is happening, it seems to me from what I read, is that by learning about outside, we're learning more about our own solar system. And it's as if when the microscopes came in the 17th century, there was a whole new world opened up, a completely new world, which influenced every person's life, from medicine to chemistry to everything. And this is a whole small world. This is a whole new big world opening up.
Yeah, I mean...
But what is it saying? What is it saying about us?
It's saying a lot about how our own solar system formed and our ideas about how that happened. Because certainly when each of us were studying and learnt about how solar systems form, there was only one example. We now know that that's not characteristic. Our solar system does not set the blueprint for how a planetary system develops around a star. There are many different ways that it can develop, from these hot Jupiters, maybe these migration mechanisms that Don has mentioned. Basically, we've had to revisit how a solar system forms, how that can then develop very differently from ours, and what other influences maybe come into play in it. The material it forms from, the proximity of other stars, and it's kind of throwing all of that into doubt and having to be reassessed.
If I can come into that briefly, one of the interesting things is we see this absolute zoo of exoplanets, yet they all result from the same basic process, which is basically the same process that forms stars. And this is in itself an interesting observation. It tells us that the process has many possible outcomes, and our solar system is just one of these. One of the things we want to learn is how frequently the planet formation process gives rise to a solar system like ours. But we also need to basically be able to chart all the possible results of the planet formation process.
A lot of people would be interested, as I am, and I presume you are, finding a planet that would sustain life. How are you getting on with that, Don?
Habitability, that's another question. So I think one of the great things about exoplanets is that it's brought together and given fresh impetus to studies of stars and also studies of what makes a planet habitable. And there are lots and lots of factors which we're really beginning to understand. If you take our solar system, for instance, how important has it been to have a planet like Jupiter? Jupiter has deflected comets which could have bombarded the Earth and could have made life extinct, possibly. What about the Moon? How important has the Moon been? So that there are lots of factors that determine habitability that we're only beginning to really just look at now. But
on the other hand, comets were useful because they brought ice, which brought water, and so on.
They moved the water around. Some people say they brought they brought the bugs around as well that led to...
Fred Hoyle was derided for doing that, and now it's coming in again. Pity he's dead.
Well, that happens to a lot of great scientists. They come up with ideas that are too advanced for their time, and it's only after their time it's picked up. So habitability is... I mean, I find it amazing that in our lifetime, for instance, we could develop the technology to be able to look at planetary atmospheres sufficiently well that we could, in an Earth analogue, look at the atmosphere and look for signs of pollution. What better sign of habitability or habitable life would there be?
Can we dwell on this for the rest of what we've got of the programme? So, many people listening will have been told, as I was told, that one of the things that distinguished Earth was the number of fine and delicate decisions that it made, the combination of non-comets, but comets, atmosphere, this time, this distance from the sun. There were so many, it was almost an accident. In fact, it was an accident, and it was a unique accident. And there we are. That was some sort of settlement which gave rise to all sorts of theories about life, and so on. You've said, Suzanne, the environment in which life might develop today does not seem all that rare.
Well, so in trying to think about how common life might be, you have to essentially line up a number of factors, and each of them you have to try and assign a probability to it, basically. And so the way at the moment we know a little bit about how many planets there are that are roughly similar to the Earth in size and in the distance from their star, so how much light they receive from the star. In order to simplify our searches for planets that might be able to host life, people have a working definition of a habitable planet, which is basically that it's got to be not too big, not too small. The reason we don't want it to be too big is so that it doesn't acquire a massive envelope of gas and the surface gravity would become too high. And the reason we don't want it too small is we think that plate tectonics on the Earth has played an important role in replenishing the carbon content of the atmosphere. So if you put that in, that gives you a range of sizes. And then we have a range of temperature because on the Earth, the early evolution of life took place in water. And if you add this as a constraint, you may be wrong, but it gives you something to start.
And are you saying that this is possible? You're finding that's possible outside that. You, Carolyn, do you want to take this up?
Well, I was just going to flag another possibility. Susanna's talking about habitable exoplanets. One thing we haven't mentioned, but could be, again, cutting-edge research over the next few years, is the possibility of exomoons. So you could have a giant planet which has large rocky moons around it, and maybe those could be quite habitable if that planet was in the temperate zone. So there's a lot...
When you say habitable, sorry, do you mean habitable by the four of us around this table, or habitable by germs and stuff?
Either. Maybe one leads to the other. I mean, I'm not going to be picky about how I define life right here. But so there are other possibilities which we have barely touched on yet.
Well, can you touch on them? Go on, you've got 2 minutes.
I'll have a go.
You
Yeah.
can do it.
Well, the diversity is just amazing. I mean, most stars actually form in binary systems, and we're now beginning to discover planets in binary systems. So just imagine that. You wake up in the morning and look outside, and there's 2 suns. I mean, that's just weird. But I think everywhere we look, I think Suzanne hit it on the head. Planets form by the same method that stars form. They're the muck that's left over after a star has been created. And they form and they move around in these systems. And if we're lucky, one of them will stop at a temperate position where in the end life could develop. So.
Suzanne?
Well, yeah, so the only other thing that I would say is in terms of searching for life, one of the most promising ways of looking for something like life, because it's very hard to define, is to look for something out of equilibrium. So, for example, the way in which we think we'll look for life on Earth-like planets in the next 20 years maybe, is to look for molecules in the atmosphere of these planets that like to react with each other. And if these molecules are present, it means something must be producing them all the time. And if there are certain combinations of molecules that we only know how to make through biological activity, that's a good signpost for life.
Well, thank you very much. Sheila Molecule, that's Suzanne Agren, Caroline Crawford and Don Palaco. And next week we'll be talking about Galen, the most celebrated and long-lasting doctor of the ancient world. Thank you for listening.
There are many more Radio 4 arts and discussion programmes to download for free. Find these on the website at bbc.co.uk/Radio 4.